Thank you, Diego, Marcon, for the introduction. Thank you for the organizing committee for this thematic session, Damião Júnior Araújo and Edgar Pimentel, and congratulations for the scientific organizing committee of the Brazilian Mathematical Colloquium. Indeed, it's my first time in this Brazilian Mathematical Colloquium, and the Brazilian Mathematical Colloquios, in fact. Well, I will talk about some recent results regarding regularity estimates for a specific class of degenerate elliptic models. Before presenting our results, let me motivate in some elliptic models. Inside the elliptic PD works, we can divide the structure of the operators into at least in two classes: operators in divergence form and non-divergent form. And inside these two classes of the structure, we can split in at least three types of the problems: uniform elliptic problem, single degenerate with the single degenerate law, and the double degenerate law. A simplest model case in the uniform elliptic case, it's a divergence of the matrix AX times the gradient of function U. In non-divergent form, you have the trace of the matrix, uniform elliptic and symmetric matrix, times the Hessian of a function U. In the single degenerate law, the simplest model case is the well-known P-Laplacian operator. Then I will restrict our analysis for the degenerate case, P greater than 2. In non-divergent form, the more simplest single operator with the single degeneracy law, it's this kind of the operator, the uniform elliptic part times the modulus of the gradient of power P. The P, it's a positive number. But in the double degeneracy law, we have, in this case, nowadays, the well-known, the PQ Laplacian. The PQ Laplacian, it's this operator where the P is greater than 2 and the less than or equal Q. But what happens when you think about the non-divergent form operator with double degeneracy law? In this case, appears arising our study this class of the operator. We have a second order operator in uniform elliptic fashion, and a scalar vector field with the double degeneracy, where the P is positive, less than equal, strictly less than the Q, and the modulating function in this case, the A, it's a non-negative continuous profile. This is exactly, when you compare with the PQ Laplacian, a non-divergence counterpart for the certain variational problems from the calculus of variation. Concerning these problems, we have a huge literature about double phase problem. Double phase problem consists in studying minimized for this class of the functional. This class of the functionals appears in material science, for example, in studying behavior of certain strongly anisotropic materials, applications in elasticity theory, in transition flow, among others situations. And then we must quote the old and new contribution. For example, the old contribution, we can see the Uraltseva, Tova, the first work in this direction, a very known work, celebrating work due to Zykov in regarding the recent contribution. We must go to the Cristiana De Filippis, Paulo Marcellini, and Giuseppe Mingioni contributions. Then in our talk, we will consider fully nonlinear elliptic models with double degeneracy, so non-homogeneous degeneracy. We have a second order operator, F. It's the lambda small lambda big elliptic operator. What means this notation? The operator is Lipschitz in the matrix variable. Has omega continuous coefficients, the supremum, when you look for the coefficient has a uniform universal modulus of continuity. The right-hand side, it's a continuing bounded profile, and this scalar vector field, it's comparable below and above. For the model case, this is scalar vector field. Before starting and in presenting our results, let me present some other motivations. When you looking for sharp regularity estimates for elliptic problems, we have focus on taking into account two specific aspects of the problem. The first one is concerning the a priori estimates for the homogeneous problem with frozen coefficients. Because when you invoke a perturbative theory, we must compare our solutions of the solutions of the homogeneous problem with frozen coefficients. And another key information is the integrability of the right-hand side. And in this aspect, we can consider, for example, these scaled and normalized profile, where kappa is a constant between 0 and 2. When you compute exactly the PDE what V satisfies, V does not satisfy the same PDE, but satisfies a PDE with the same properties in the following sense. The matrix rho, it's not the same matrix, the scaled matrix, but remains in the same class, remains with the same modulus of continuity. In the right-hand side, it's a scaled right-hand side. F, it's not the same right-hand side, but depend on the kappa, remains in the same integrability space. When you put together these two informations, we conclude the following things. When you increase the integrability, they increase the regularity of the coefficients, this is implied better local regularity for the solution. These two aspects, you improve the regularity of the coefficients, increase the integrability of the right-hand side, you increase or improve the regularity of your corresponding solutions. For example, you can classify all the ranges of the regularity regimes for this problem. When the integrability belongs to range, solutions are C1 zeta with a explicitly modulus of continuity. These borderline case solutions are not Lipschitz, but almost Lipschitz, are log Lipschitz continuous. In these regularity regime solutions, the gradient of the solution has a Rhodes modulus of continuity. In the regime of the right-hand side, L infinite or BMO solutions are almost C11. Indeed, are C1 log Lipschitz, for example. In this case, the analysis is under viscosity solution. This is a formal definition of the viscosity solution. Daskalopoulos, Kuzi, and Mingioni have proved similar results for the borderline case, the C1 alpha regime. But what happens when you consider degenerate operators? In the single degeneracy law, when the A is 0, and Berindelli, de Mengel, and the inverse Silvestre proved C1 alpha regularity estimates. In the double degeneracy regime, Cristiana de Philippis recently proved C1 gamma locally regularity estimates. But de Philippis leaves some open issues regarding the general scenario. For example, the sharp regularity comes in relation to the sharp regularity for the viscosity solution. Concerning the regularity theory for the uniform elliptic case, when this field, vector field, it's identically 1, we have the Caffarelli-Trundiger classical results in these articles and book. Then our goal is prove the sharp regularity for this class of the problems. When you invoke the structural conditions, then solutions are C1 minimum between 1 over P plus 1 and alpha homogeneous means. Alpha homogeneous means that we can select any number between 0 and the alpha homogeneous. Alpha homogeneous is the Holder exponent for the gradient of the solutions of the homogeneous problem with constant coefficients. When you compare our approach of the De Philippe's approach, we have three significant differences. In the De Philippe's approach, she used the compactness coming from the Cauchy-Young's method. We can use, for example, compactness coming from the Harnack inequality and Holder regularity. C1 alpha regime for the Cristiano De Philippe's appears in a fine approximation scheme, like a deviation by plans. She considers switched problem as something and in such a way. And concerning the degeneracy of the degeneracy character of the operator, De Philippe's split the analysis in two cases, where the switched parameter is small or large. In our case, we split the analysis in two cases, when the gradients of solutions are small or large. Then our approach was inspired in the following reference, the following articles. A beautiful article due to Araújo Teixeira Urbano, a very nice paper due to Lindgren and Litkvist, and another one due to Atoch, Parvian, and Brotsinoj. We use the strategy in coming from these works. Our main result is the following. It's a joint work with Gleidson Chaves Ricarte from Universidade Federal do Ceará. It says the following: any viscosity solution of our original problem is C1 alpha, where alpha is the minimum between 1 over p plus 1 and alpha homogeneous minus, and satisfies the following estimates, where this term means this semi-norm, and the LEX0U is the Taylor expansion of U up to the first order. This is a natural extension of the recent article due to Araújo, Ricarte, and Teixeira. These regularity estimates play a fundamental role, for example, in establishing blow-up and Liouville type results, with geometric properties and house of measure estimates, and sharp regularity in some free boundary problem. For example, Bernoulli type, obstacle type is singularly perturbed problems. Here I quote some examples where sharp regularity estimates play a fundamental role. This article due to Anderson, Lindgren, Chagolin, a classical book due to Caffarelli Salsa. This article joint work with Ariel Salor from Universidade de Buenos Aires, and a recent work joint work with Elson Cesar Jr. and Gleidson Chaves Ricarte. Let me present some useful mathematical devices in our approach. For example, we need a ABP type estimate. ABP ensures that the L infinite norm is controlled by the data of the problem. The L infinite norm of the boundary, the LEN norm of the right hand side, times this quantity. Holder estimates the C0 alpha prime norm. It's under control in terms of the L infinite norm of the solution in this term, where appears the influence of the right hand side, the influence of the modulated function, the influence of the exponents P and Q, of course. Stability result. Stability result, it's exactly, we have a family of the PDs, a sequence where the UK, FK small, capital FK converse, then roughly speaking, you can pass the limit in the P. Summarizing. A invert Silvestre cutting lemma means the following. We have the homogeneous problem with the double degenerate signature. Then, roughly speaking, you can cut the influence of the double degenerates. Then solutions of this problem are solutions to the uniform elliptic problem. Literally, we can cut the degeneracy signature of the problem. And the De Philippe's, at last but not least, the De Philippe's a priori estimates. The solutions has a C1 gamma norm under control. We can find these results in this reference, for example. This recent reference, joint work with Fernán Vivas from the Universidad de Mar del Plata, Argentina, in the Cristiano de Phillips manuscript. Let me know my time, okay. Then the first step in assessing our regularity estimates is employ approximation regime. The approximation regime consists in approximate solutions of your problem to solutions of the homogeneous problem with constant coefficients. It says the following: give me any normalized solution, then for all error, there exists a quantity, delta, such that the oscillations of the operators, the right-hand side is small enough, then we can find a good profile, good in the following sense, have the good a priori estimates, such that in the C1 topology, solutions are close of this good profile. The proof consists, just waving hands, the proof consists in a reduction to absurd argument in use, for example, compactness, stability, the a priori, the Phillips a priori estimates, the invert Silva-Slamy, the uniqueness of the derivative problem. It's a very classical proof I cannot reproduce, but it's classical in this sense. These assumptions, the normalization in the smaller regime, are not restrictive in the following sense. We can perform a normalization in scaling such that the V, the F, and the oscillation of the coefficients fall into the assumptions of the previous line. Then we can perform a normalization in flatness regime. Then the approximation lemma implies a C1 closeness combined by the a priori estimates, implies that each solution is geometrically close to their tangent plane in this sense. Then under the assumptions of the previous lemma, we can put the U inside the ball of the radius R, center of the X0, close your tangent plane, where the radius is a fixed constant in this range. Observe this appears the influence of the alpha homogeneous constant, the a priori estimates. And this is exactly a first step in a possible interaction procedure. In elliptic regularity theory, when you wish to prove C1 alpha estimates at X0, you can find a sequence of the affine functions such that in its whole K level, you can approximate U in the following sense. But we have an obstacle here. Our original operator, it's not in translation invariant for this affine function. When you compute the PDU that this profile satisfies, we can't recover or associate to the original PDE, for example. Then you overcome this obstacle, performing a new oscillation mechanism inspired of the Araújo, Teixeira e Urbano article, for example. In the first level, you can compute this oscillation, where the influence of the gradient is coupled inside the oscillation. And we proceed with the interaction process. In a first step, we have these estimates. We have a correct geometric decay in terms of the radius of the ball and the radius of the ball times the magnitude of the gradient. Then the oscillation of the U depends on the magnitude of the gradient. Then we perform the interaction process. In a K-level step, the geometric approximation, the geometric iteration produce these estimates. We can prove this via a induction process. In this moment appears the second restriction under the exponent. Alpha is less than or equal 1 over p plus 1. What means the influence of the magnitude of gradient? In this case, we decompose our analysis in two cases, where the gradient is large and in the points where the gradient is large, the points where the gradient is small. But larger is small in a very specific sense. We define the singular zone of, such that the point such that the gradient is less than the radius of the ball times to our magical exponents. Then we can prove not this discrete iteration. Before we prove this discrete iteration process. Here we prove a continuous discretion, this continuum estimates in the following sense. For all radius rho 0 between 0 and the original rho 0, we can prove the oscillation of the U is less than a universal constant, the rho to the correct power, 1 plus alpha, times this term. This is a key point. If the x0 belongs to the correct singular zone, this quantity is under control. This is exactly the key point in the proof. In order to prove the theorem, we can suppose, without loss of the generality, the compact is the ball B1/2, x0 is the origin, belongs the singular zone. When you compute the seminar, then you use triangular inequality, invoke the previous lemma, and use that the x0 belongs to the singular zone. Then this quantity is under control. Then inside the singular zone, we prove our C1 alpha estimates. But what happens outside the singular zone? Outside the singular zone, we have the following. The gradient is bounded away from 0 and infinity. Then we can invoke the Caffarelli-Tröndiger classical results. Why? Because the operator becomes uniform elliptic. In the uniform elliptic scenario, we can invoke the Caffarelli-Tröndiger, or if you prefer, the Teixeira's classification result. Let me come back for the double phase problem. In the double phase problem, Maria Colombo and Giuseppe Mingioni proved that minimizers of the double phase problem satisfies the R PQ harmonic functions and are locally C1 alpha 0. Then we can decompose or expand this operator in non-divergent form. You the LW is J1 plus J2. J1 is our operator, where the Laplacian is the trace of the Haitian. The J2 is the bad part. If the bad part is a L infinity profile, we can invoke our previous result in the following sense. Then it's sufficient to suppose in this case that the normalized infinite Laplacian, the gradient of the modulating function, and the gradient of the solution are L infinite, then we can invoke our previous results in the following sense. Solutions are locally C1, 1 over P minus 2 plus 1. In other words, 1 over P minus 1. This is slightly similar for the exponent that appears in the CP prime conjecture, for example. Then we can this table of the classification and some open problems yet. For example, we don't have a Calderon-Zygmunt type estimate for this class of problem, but a very interesting question arises. What happens when you consider, for example, this specific class of the right-hand side? In this specific class, the right-hand side, it's exactly the dead core solutions, for example. The mu is the positive constant, it's strictly less than P plus 1. F0 is the non-negative bounded away from 0 and the infinite profile. Then what happens when you stop in a point of the free boundary? In a point of the free boundary, we prove unspectable gain of smoothness in the following sense. Solutions decay in this order. What is the magical information in this exponent? This exponent is strictly less than the 1 over 1 plus 1 over P plus 1. In this exponent, it's the better regularity result when you are, for example, in concave or convex operators. Then, of course, we can assume here if it's concave or convex, but along free boundary points, we obtain this gain of the smoothness. We obtain a upper bound control yet. Geometric non-degeneracy result in the following sense: the supremo over the boundary of any ball with small magnitude, it's greater than a universal constant, depending on these constants, the radius of the ball to the magical power. The proof employ a comparison principle like the one the Berindelli mentioned works applied for these two profiles. And in order to finish, we can also prove regularity results for these elliptic PDE models. In this case, with variable order. We prove existence, uniqueness, uniform boundless, global compactness, Holder and Lipschitz, gradient estimates, improved local and sharp global, geometric non-degeneracy, fine estimates in some applications, and nonlinear modes and free boundary problem, just to mention a few connections. This is a joint work with Elson César from UFC, Universidade Federal do Ceará, Gianni Rampasso here, Universidade Campinas, Unicamp, and Gleison Chaves Riccardi, also from the USA. You can understand these results with a natural extension for the recent results due to Berindelli dimension, global estimates for the constant exponents, Bronze, Pimentel, Rambassi, Teixeira for the single degeneracy law, but with variable ordered fashion, and the Fan Gradulescu for the local estimates for the non-homogeneous degeneracy with variable order. Thank you very much for the attention, and I hope see everybody as soon as possible here in the Unicamp or around the world. Thank you.